In this hands-on, we will show you the code and the resources related to BlockFLsim, and we will make some simulations to show how the simulator works. First of all, let me introduce the structure of the project, as several resources can be found there. First, we have 4 main folders with different types of files. So in database, for instance, you will find some results that we have collected in our previous experiments and works. And in this case, we have some outputs that we used in a recent publication. We also added here the scripts that we use to generate these outputs. Then in database processing, we store all the complementary code, not necessarily in Python, to process the outputs and, for instance, generate plots in this case. So far, we have some MATLAB scripts that generate the plots related to the outputs that we have in database. In resources, we may have related files like images, guides, and so on. But so far, we have only included a diagram and the plots generated with the code in database processing. And finally, we have the source folder where the simulator lies. So the core of the simulator can be found in several files, which implement all the logic that we need to simulate a blockchain-enabled FL application. We have files like events and scheduler that handle all the events of the simulator, including the creation of events, queuing management, and so on. Then the implementation of blockchain layers and FL functionality can be found in models, where it is defined the structure of blocks, transactions, and nodes, and also the logic related to consensus, incentives, and network. As you can see, the implementation of different blockchains is done by extending the basic modules and by adding a few more. For instance, if we focus on the Bitcoin implementation, we can see that it has its own consensus and node implementation, and it also defines the way of generating and handling blocks according to proof of work in this case. In contrast, the implementation of Ethereum provides features like the modification of transactions to include gas fees or gas limits and so on. Regarding the specific use case of FL, we included 2 different files here in models. One is federated learning, which provides methods for loading datasets, processing the datasets, federating data, creating FL models, or executing model training and model aggregation. And then we have another important module, which is PyTorch models, which contains the different ML models to be trained on different datasets. The available datasets can be found in the data folder, and here we have Cipher, MNIST, Extended MNIST, and MNIST. But other datasets can be added, and some of them are added automatically by the federated learning module, like Fashion MNIST, but we don't have it downloaded now here. To run the simulator, we need to focus on these 2 files, input config and the main file. So the inputs config file, it contains all the simulation parameters, and the main provides all the instantiation of the methods and variables and includes all the logic to start generating and handling events. So let us first focus on the inputs config file. Here, as you can see, the configuration of the simulator is done differently for each blockchain model. In our case, we focus only on FL chain, which uses proof of work and runs federated learning. And this method has been extended from the existing Bitcoin one, which is original from BlockFLsim. When we scroll down to the FL chain model, we see that we can customize some parameters related to the FL operation, including the type of federated learning. So far we have synchronous and asynchronous implementations, the datasets that we would like to use, the total number of clients, the number of clients that are selected per each iteration, the number of epochs, the batch size, and so on. There are other parameters that have an impact on FL application, like the client's computational power, which affects the periodicity at which FL devices can provide updated local models. But then we have other parameters related to the blockchain network. In this case, the number of blockchain devices is set to the number of FL devices, but the number of miners can be customized. So for instance, we can have a network of 100 federated learning devices which also participate in the blockchain, but only 10 can be miners as specified here. Apart from that, there are other parameters for transactions and blocks like the size of a transaction, the mining rate, aspects related to mining rewards, and so on. Finally, we have the simulation related parameters like the simulation time, the number of runs for the same scenario, the usage of GPU or not for training, and the enabling, and if we want to enable or not logs. Regarding the main file, let us take a quick overview. So when running this file, the first thing to do is initializing all the models and variables. And this is done for each blockchain model. But here we focus on FL chain 1, specified as model number 4. Then, so after the initialization, it begins with the creation of events by invoking some functions so that FL devices can start planning models and uploading them to the blockchain to be later aggregated, and repeat this process until convergence or until the simulation finishes. Regarding the FL part, this is where we initialize the FL models and datasets for each client. So depending on the dataset, we may invoke one ML model or another, which are prepared for receiving different inputs, like the set of bits conforming an image, and also providing different outputs, like classifying between 10 classes or 100 classes, or whatever your application is doing. Once models and everything is set up, we start handling the events through this function, handle event function. So depending on the event, a different action will be triggered. For example, when a new block is propagated, FL devices may download it and generate the next local model with the information, with the updated information in the global model, in the block, I mean. I will not go through the implementation details of FL operation, but here we have two cases. Synchronous FL, whereby FL devices are orchestrated and can receive only the models from the main chain for training, so this is completely synchronized. And asynchronous federated learning, whereby FL devices may access the blockchain at any time to retrieve to take the latest model from its closest miner. So you may notice that with this implementation, we are able to capture the temporary inconsistencies that arise from decentralization of a blockchain, including block propagation effects or temporary forks. So at the end of the simulation, when the maximum time is exceeded or when there are no more events in the queue, we gather and post-process several useful statistics. Some of them are inherited from the original BlockFLsim implementation, but we added a few more things for performance analysis of federated learning. So now let us run a simulation, which in this case we can customize by using the input config file. We can set the total number of nodes to a low value to speed up the simulation time, and change other things like the number of epochs or the total number of users for testing our ML solution. But here, of course, notice that the more users we introduce, the more computations will need to be done. So these computations include many things like the creation and propagation of transactions, the computation of local models, or simply the evaluation of models at different clients. So the more users, the more overheads that we are adding, so the higher the simulation time will be. And finally, we can also tune blockchain parameters like the block interval. So in this case, let us use a high value like 60 seconds between blocks. So now with this configuration done, we may start a short simulation to show you the outputs of the simulator in this case. So we can do the simulations in two different ways. One is by directly executing the main FL chain file, which takes the information that we put in the input config file directly and runs on the simulation. And the other thing is by executing a script which provides several parameters as arguments, and this allows us to make like several computations, several simulations with only one instruction. So we don't need to execute and customize the main file with several inputs to do this, no? But first, let us run the main. So we can go to the console and execute it, or in my case, we can simply execute it from the IDE. Here, when the simulator begins, we can see some information like the main input parameters. In this case, we have dataset type 1, which is MNIST. We have the total number of clients, the number of clients that we use per epoch, the number of iterations of federated learning, and also the client's computational power and other things, right? So another log that we have here is related to the dataset. So basically here we have information about the number of samples that we used for training, the number of samples that we use for validation and for testing. So as the simulation progresses, you will see that we are displaying or not the different events depending on if we have enabled logs or not. But basically at the end of the simulation, we will gather different types of outputs. One is in logs, since we save also the log file into a txt, and the other is an Excel file that kind of collects and summarizes how the simulation went. So if we open one of these Excel files, we may see different parameters. So here we have like different tabs. The first tab is like the configuration of the system with very few parameters like the block time, the block propagation delay, the number of miners, simulation time, so on. Then we have a very brief summary of how the simulation went in terms of number of logs that have been generated, number of on-call blocks, and so on. Then we have a tab for the profits. So the profits depend on how many blocks each miner has mined. In this case, we do not consider this. And here in the chain, we have other useful information because we have the information related to the main chain. So we have things like the block ID, which is the previous block, also the timestamp of the block, the miner ID, the miner who mined this block. Then we have the number of transactions in the block size as well. And we also have other information now related to the FL operation. So here basically we added several parameters. One is the block age. Then we have also validation accuracy, validation loss, test accuracy, test loss, which depend on the different data sets that we have split, no? Because we have training, test, and validation data set. So here is where we put the accuracy of the global model contained in each of the blocks that we have mined, in this case in BlockFLsim. We also have a tab for the asynchronous implementation, which is called federated learning. And here we collect basically the test accuracy of every single FL device participating in the FL operation for each single epoch that we have considered. So in this case, we can notice the asynchronicity because some of the users are not not all the users have the same number of measurements, because not all the users accessed to the same blocks or delivered local computations on time. And this is basically to keep track of the individual performance of FL devices when they participated in this distributed, decentralized, federated learning optimization. And for completeness, we have a different another tab which we call other. At the moment it is not very complete, but we have other statistic measurements here, like the mean time for mining computed by each time we provide the computation for the mining time at every miner. So we compute the mean value here. In this case, since we only had like 3 epochs, so the main chain is quite short, the mean mining time is not very representative. And that's all. The other way of executing the simulator is through these scripts, where basically you can set arrays of different parameters, like the total number of clients. You could test like different values for this, or you could test also different blocks intervals. And when executing this, you got all the simulations done at once, so that you can collect the outputs from each specific simulation in the output folder as well.